Okay, so students, let us start today with diagonalization of a matrix. For that, let us discuss first what is a diagonal matrix. Suppose if I write E matrix as this, in diagonal we have non-zero elements 1, 2, 3, and other elements are all zero element. Okay, then it is called a diagonal matrix, as in diagonal only we have non-zero elements. Therefore, is definition of diagonal matrix, we can say that all the entries except the diagonal entries are 0. If this happens, then we can call it a diagonal matrix. Now let us talk about identity matrix, students. Suppose identity matrix of order 3, then we know it is nothing but 1 0 0 0 1 0 0 0 1. So identity matrix is actually special type of diagonal matrix for which diagonal entries are 1. Now suppose let me talk about a matrix B, suppose which is 1 2 3 5 7 9 10 14 15. Now can we convert this matrix B to a diagonal matrix? If we can convert it to a diagonal matrix, then we say B is diagonalizable. Otherwise, it is not diagonalizable. Okay. So, let us talk about now the terms what we need for diagonalization, that are eigenvalues and eigenvectors. See students, suppose we have a matrix A, a vector alpha. If A alpha equals to lambda alpha, where lambda is a scalar, and alpha is a vector, then alpha is called eigenvector and lambda is called corresponding eigenvalue. Okay, now see, from this condition A alpha equals to lambda alpha, if I rewrite in this form, A alpha minus lambda alpha equals to 0, then we can write A minus lambda I into alpha equals to 0. From here we get our characteristic equation, which is determinant of A minus lambda I equals to 0. Now we have statement of Cayley-Hamilton theorem in our syllabus. Cayley-Hamilton theorem says that every matrix should satisfy its own characteristic equation. Okay, so students, let me take one matrix for which we are going to find characteristic equation. Let us take matrix A2 as 1 0 2 0 minus 1 1 0 1 0. Now see, I have written that our characteristic equation is determinant of a minus lambda I equals to 0. So we are going to find a minus lambda I equals to 0, right? This is our characteristic equation. Now see students, A2 is a 3 cross 3 matrix. So whenever we are considering I will be of order 3. Now I is actually identity matrix 1 0 0 0 1 0 0 0 1. Now if I multiply lambda with it, that means it will become lambda 0 0 0 lambda 0 0 0 lambda. That means if I write a minus lambda I, that means I am subtracting lambda from the diagonal entries only. So therefore, whenever we are going to write a minus lambda I equals to 0, we will only subtract lambda from the diagonal entries of A. Okay, so therefore we are getting this. Now we have to find what? We have to find determinant of this. So therefore, determinant of a minus lambda I, that is equals to determinant of 1 minus lambda 0 2 0 minus 1 minus lambda 1 0 1 minus lambda. Okay, so let us evaluate this matrix, that is 1 minus lambda into minus lambda into minus 1 minus lambda minus 1, then 0 into its minor, that is 0, and 2 into this, 1 into 0 0 into this, so that is also 0. Therefore we are having this. Therefore our characteristic equation is nothing but a minus lambda I, that is equals to 0. That means 1 minus lambda into, if I calculate this side, this is lambda into 1 plus lambda minus 1 equals to 0. That gives 1 minus lambda into lambda square plus lambda minus 1 equals to 0. Now see, therefore this is actually our characteristic equation. This is the characteristic equation we are getting. Now from here, if we want to find eigenvalue, then 1 minus lambda equals to 0. This gives lambda is equals to 1. Now for lambda square plus lambda minus 1 equals to 0, let us put it into Bhattachajee formula. So that will be minus b, that is minus 1, plus minus root over of b square, that is 1, minus 4ac, so 4 into a is 1, c is minus 1 by 2 I say, so 2 into 1. Okay, so therefore it is minus 1 plus minus root over of 5 by 2. Therefore our eigenvalues are 1 minus 1 plus minus root 5 by 2. Okay, we are getting 3 eigenvalues from here. So now we know how to find characteristic equation and how to find eigenvalue. Okay, so let us check Cayley-Hamilton theorem. Cayley-Hamilton theorem says that every matrix will satisfy its own characteristic equation. Let us take it for this matrix A3, that is 0 0 1 3 1 0 minus 2 1 4. We have this matrix. So let us find the characteristic equation first. For finding characteristic equation, we know we have to find a minus lambda I is equals to 0, And as we have discussed previously, let us just subtract lambda from the diagonal entries and write down the matrix in determinant form. So if I expand the matrix, it is minus lambda into 1 minus lambda into 4 minus lambda, then 1 into 0, then 0 into its minor, that is 0. So now we have 1 into, this is 3 minus 2, that is plus 2 into 1 minus lambda. This equals to 0. Now minus lambda, this is 4 minus 5 lambda plus lambda square, plus this is 3 plus 2 minus 2 lambda equals to 0. That is minus 4 lambda plus 5 lambda square minus lambda cube plus 5 minus 2 lambda equals to 0. Now see, we have 5 lambda square, then minus 6 lambda, we have lambda cube also, so minus lambda cube, then plus 5 lambda square minus 6 lambda plus 5 equals to 0. That is lambda cube minus 5 lambda square plus 6 lambda minus 5 equals to 0. Now see students, Cayley-Hamilton theorem says what? That every matrix should satisfy its characteristic equation. That means a cube minus 5a square plus 6a minus 5i, this should be equals to 0. Okay, in place of lambda, if I put a, then it should satisfy the equation. So let us check for that. For that we need to know a cube, also we need a square, right? So let us find a square first. Let us write down our matrix again. Our matrix A3 is this 0 0 1 0 0 1, then we have 3 1 0 and minus 2 1 4. Let us find A3 square. Okay, so that is 0 0 1 3 1 0 minus 2 1 4. Now if I multiply this row with column, then it is 0 into 0, that is 0, 0 into 3, that is 0, 1 into minus 2, that is minus 2. Then 3 into 0, that is 0, 3 into 1, that is 3, 0 into something, that is 0, so therefore 3. Now multiplying with this, so minus 2 into 0, that is 0, 3 into 1, that is 3, and 4 into minus 2, that is minus 8, so 3 minus 8, that is minus 5. Then let us multiply with second column, so 0 into 0, that is 0, 0 into 1, 0, 1 into 1, that is 1. Let us multiply the second row, 3 into 0, that is 0, 1 into 1, that is 1, and 1 into 0, that is 0. So minus 2 into 0, that is 0, 1 into 1, that is 1, 4 into 1, that is 1, 1 plus 4, that is 5. Now I am multiplying with third column, this one. So 1 into 0, that is 0, 0 into 0, then 1 into 4, that is 4. Now 3 into 1, then 1 into 0, then 0 into something, so that is 3. Now minus 2 and 0 and 4 fours, that is 16. So 16 minus 2, that is 14. Now we have to find what? Now we have to find A3 cube, that is minus 2 1 4 3 1 3 minus 5 5 14 along with 0 0 1 3 1 0 minus 2 1 4. So I am multiplying the first row with the first column. Minus 2 into 0, that is 0. 1 into 3, that is 3. 4 into minus 2, that is 8. So 3 minus 8, that is minus 5. Again I am multiplying 3 1 3 with this. So 0 into 3, that is 0. 1 into 3, that is 3. Then 3 into minus 2, that is minus 6. 3 minus 6, that is minus 3. Then 5 into 0, then 5 into 3, that is 15. 15, this is 15. Then 14 into minus 2, that is minus 28. That is minus 13. Now let us multiply with the second column. Okay, so 0, then 1 into 1, that is 1. 1 into 4, that is 5. Now 0, then 1 plus 3, that is 4. Then 0, this is 5 plus 14, that is 19. Then minus 2 0 16, that is 14. Then 3 plus 12, that is 15. Then minus 5 that is 51. We have this. Now let us put it into characteristic equation. So a cube minus 5a square plus 6a minus 5I we have. So let us write a cube minus 6a, not 6a, it is 5a square. So we have minus 5a square plus 6a minus 5I. Let us take LHS. So a cube is minus 5 5 14, minus 3 4 15, minus 13 19 51, minus 5a square. So 5 into a square is minus 2 1 4 3 1 3 minus 5 5 14. Then we have plus 6 into a is 0 0 1 3 1 0 minus 2 1 4 minus 5i. So 5 into 1 0 0 0 1 0 0 0 1. We have this. So let us write this. Minus 5 5 14, then minus 3 4 15, minus 13 19 51, minus, if I multiply all the things with 5, then it is minus 10 5 20, 15 5 15, minus 25 25 70, plus 6 0 0 6 18 6 0, minus 12 6 24, minus 5 0 0 0 5 0 0 0 5. Now let me add this one with this one. So we have minus 5 minus 5, 14 plus 6, that is 20. Then we have minus 3 and 18, that is 15. Then 4 plus 6, that is 10. Then we have 15. Then minus 13 minus 12, that is minus 25. Then 19 plus 6, 25. Then 51 plus 24, that is 70. And let us add these two. Therefore we are getting minus 10 5, that is minus 5. Then we are getting again minus 5. Here we are getting plus 5. Then 20. Then we have 15 0. And then if I add this, I will get here will become 5, then 20, then 15, then 5 5, that is 10. Now we have again 15, then 25 minus 25 plus 0, that is minus 25, 25 70. So if I subtract, I am getting 0. Therefore we can see that every matrix satisfies its own characteristic equation. So that's how in the examination, if there is given that prove Cayley-Hamilton theorem for a given matrix, we have to do it like this. So we have already discussed about Cayley-Hamilton theorem. We have talked about characteristic equation of a matrix, and also we have found how to actually derive the eigenvalues. So let us discuss about eigenvectors right now. Suppose we have a matrix which is 2 cross 2, that is 4 2 3 3, and we have to find eigenvectors for this given matrix. So students, the process is same. First of all, we have to find the characteristic equation. So let us find a4 minus lambda I, determinant of that equals to 0. Okay, so that is nothing but a minus lambda 2 3 3 minus lambda, that equals to 0. That gives 4 minus lambda into 3 minus lambda minus 6, that is equals to 0. That is 12 minus 7 lambda plus lambda square minus 6 equals to 0, which gives lambda square minus 7 lambda plus 6 equals to 0. Now see students, let us find eigenvalues from here. So lambda square minus 7 lambda plus 6 equals to 0. If I do middle term, lambda square minus 6 lambda minus lambda plus 6 equals to 0, which gives lambda minus 6. If I take minus common, then it is lambda minus 6 equals to 0, which gives lambda minus 1 lambda minus 6 equals to 0. That is lambda equals to 1 and 6. Now as we have different eigenvalues, if we have different eigenvalues, then only a matrix is diagonalizable. So the first condition for diagonalization of matrix is eigen values are different. Okay, so this time we have different eigenvalues. We have 1 and 6. Now we have to find what? We have to find eigenvectors. Okay, we have to find this. So let us start. We know that a minus lambda I into alpha, that equals to 0. We have talked about this, and from here only we get our characteristic equation, right? So therefore let us find this for lambda equals to 1. Okay, so as we have 2 cross 2 matrix, therefore what will be our alpha? Our alpha will have 2 unknown, x1 x2. So let us put, we have a matrix as 4 2 3 3. We are going to find a minus lambda I, so therefore lambda 0 0 lambda, this into alpha x1 x2, that equals to 0. So from here we are getting 4. If I put lambda equals to 1, so that is 4 minus 1 2 3 3 minus 1, that into x1 x2 equals to 0, which is 3 2 3 2 into x1 x2 equals to 0. Now see students, if I multiply, I will get two identical equation, 3x1 plus 2x2 equals to 0. If I multiply the second row, then also we will get this equation only. So from here I am getting 3x1 equals to minus 2x2, that is x1 by minus 2 equals to x2 by 3. Let us take that is equals to k. So x1 equals to minus 2, x2 equals to minus 2k, and this is 3k. Therefore our alpha is x1 x2, so therefore let us put minus 2 and 3. Now let us do the same process for lambda equals to 6. So this time it is 4 minus 6 2, then 3 minus 6 equals to 0. Therefore minus 2 2 3 minus 3, sorry, this into, there should be alpha, so into x1 x2, that equals to 0. Now this into x1 x2, that equals to 0. It also gives us same equation, 2x1 plus 2x2 equals to 0, which is nothing but x1 minus x1 plus x2 equals to 0. See, from here if I multiply the second row, we will get 3x1 minus 3x2 equals to 0, that is same as minus x1 plus x2 equals to 0. So this gives us x1 equals to x2. Let us take that equals to k2, suppose. Therefore our alpha is this time kk. If I take k common, that is 1 1. Okay, so we have two eigenvectors. First one is minus 2 3 and second one is alpha. Okay, so that's how we have to find eigenvector for corresponding eigenvalues. For lambda equals to 1, our eigenvector is minus 2 3, and for lambda equals to 6, we have our eigenvector as 1 1. Okay, Now students, if the question says that find the diagonalized matrix, find the diagonalized matrix, okay, then formula for the diagonalized matrix is P inverse AP. Okay, formula for diagonalized matrix is nothing but P inverse AP, where P is actually the eigenvector, matrix of eigenvector. So that is minus 2, 3 and 1, 1. Now see, now we have to find what? Now we have to find P inverse. So P inverse is 1 by determinant of A into adjoint A. Okay, so for 2 cross 2 matrix, it is easy to find the determinant. It is minus 2 minus 3, that is minus 1 by 5. Then adjoint A, for 2 cross 2 matrix, we know how to find adjoint A. Just exchange the diagonal elements. So 1 minus 2 and sign change for the other elements. So minus 3 minus 1. Okay, we have this. So let us now write down our diagonalized form. T equals to P inverse, that is minus 1 by 5. Then we have 1 minus 1 minus 3 minus 2. Then into A is actually 4 2 3 3, and P is minus 2 1 3 1. Okay, so let us multiply. Minus 1 by 5, 1 minus 1 minus 3 minus 2. Then I am multiplying the first row with the first column, therefore this is minus 8, then plus 6, that is minus 2. Then this is minus 6 and 9, that is 3. Then 1 1 we have, so 4 plus 2, that is 6, and 3 plus 3, that is also 6. Now let us multiply these two matrix. 1 minus 1 we have, so 1 into minus 2, that is minus 2, then minus 3, that is minus 5. Then we have this is minus 3 into minus 2, that is 6, and this is minus 6, so 0. Then this is 6 minus 6, again 0. Then minus 3 into 6, that is minus 18, minus 18. Then minus of this is 12. Okay, that is minus 30. So if I now multiply this with minus 1 by 5, I will get I will get 1 0 0 6, which is nothing but our first eigenvalue lambda equals to 1 we have got, and then we have 6. So see, in the diagonal element we have the eigen values only, lambda 1 0 0 lambda 2. Therefore this is our diagonalized matrix. Okay, so that's how we have to find the diagonalizable matrix. This is the process. Okay, so in today's class we have learned about how to find characteristic equation of a matrix. We have talked about Cayley-Hamilton theorem, and after that we have discussed about eigenvalue and eigenvectors, and if all the eigenvalues are different, then we will have diagonalized matrix. And how to find the diagonalized matrix formula is P inverse AP, that also we have discussed. Hope you find this well. Thank you students, and bye.